if we have water, and it's at a temperature, any temperature below the boiling point for a particular altitude that we're at, then we can say that in order to bring the water to a boil, a specific amount of heat is required. And this specific amount of heat is usually referred to as BTUs. Now, a BTU is defined as the amount of heat required to raise the temperature of 1 pound of a substance 1 degree Fahrenheit. So, in this case, the substance is obviously water. Now, to give an idea of the size of this volume of the pound of water, there are 231 cubic inches to a gallon. So if we take the 231 and we divide it by the pounds in a gallon, which is 8.34, we can see that the math works out like this. So 231 divided by 8.34 equals 27.7 cubic inches. So this works out to a cube about 3 inches by 3 inches by 3 inches. So it's about the size of a Rubik's Cube, just to give you an idea of how small a pound of water actually is. Now, it works like this. If we start with sea level figures and we have 1 gallon of water and it's currently sitting at room temperature of say 70 degrees and we want to bring it to a boil, we have to find out the specific amount of heat required to bring it to a boil. So this is called specific capacity. So water boils at 212 degrees. You subtract the water temperature of 70 degrees and you get 212 minus 70 equals 142. Well, that's 142 BTUs. That's a specific amount of energy that's required to raise that 1 pound to the boiling of water to its boiling temperature. So to find out the specific capacity of BTUs, you multiply it by 142 times 8.34. You get 1184.28 BTUs total specific capacity to bring the water from 70 degrees to its boiling temperature, 212 degrees at sea level. So what about higher altitudes? Well, you'd need to do a little math, but water boiling temperature changes. That is that it reduces by about 1.84 degrees per 1,000 feet. So you figure the new boiling temperature like this. If you're at 8,000 feet, you divide 8,000 by 1,000, you get 8. Take 8 and multiply it by 1.84, you get 14.72. This means that you subtract the 14.72 from 212 to get 197.28 or 197.3 degrees. So back to our original 1 gallon of water at 70 degrees, then we'd need 130 BTUs. So 130 times 8.34 equals 1,084.2 BTUs. So you need less BTUs to heat the water to boil, but it also takes longer at higher altitudes because your flame does not burn as hot as it would at sea level. Now this is if you're on a stove or something like that. Now, if we continue on, what about after it's boiling and we see steam? Well, we can actually absorb more heat in BTUs without a continual rise in temperature. This is now called latent heat of vaporization. And when water freezes, it's called the latent heat of fusion. There is actually an additional 970.3 BTUs worth of energy that can be absorbed by water when it passes from the liquid to the gas, that is the vapor stage. How much energy in BTUs actually? Well, if we go back to our 1 gallon example, we have 8.34 pounds in the gallon. If we take that 8.34 pounds and we multiply it as we did before, but only this time we're going to use the latent figure of 970.3, we will get 8,092.3 BTUs. So in the conversion, once it's boiling and it goes to steam, we just absorbed an additional 8,092 BTUs. If we add the two final answers together, we will get what is called thermal capacity. So you have specific capacity, you have latent capacity, and then you have the thermal capacity. The thermal capacity is the combination of both. So there is the three terms. Specific capacity, which is the specific amount required to boil water. The latent capacity, which is the required amount if we want to take full advantage of heat absorption and make good steam. And then thermal capacity, which is the sum total of both BTU capacities. So how does this help us in firefighting? Think of it like this. If you want to boil water, you apply a lot of heat to it. Well, that's what we want to do. We want to boil water in wildland fires. And why? Because it absorbs heat, a lot of it. What happens if we take heat out of a fire? It goes out. How does this help us with our engine and nozzle? Well, we'll take a look at the next example. And so the next example that we have deals with this. So if we're flowing a 30 gallons a minute and we have a tank temperature of 50 degrees, then we have to convert the flow in gallons per minute by the pounds per gallon to equal the pounds per minute. So gallons per minute times pounds per gallon equals pounds per minute. So here you can see we got 250.2 pounds per minute when we flow 30 gallons a minute. So now we have what's called boiling and steaming. If we take our boiling temperature, okay, of 212 and we subtract 50 degrees from it, we have a specific heat of 162. Then what we'll do is we'll apply that over here, specific heat, multiply it by our pounds per minute, and we get 40,502 BTUs per minute. That's the BTU content in raising the water temperature from 50 degrees to the boiling temperature 212 at sea level. Then if we go from boiling and turn it into steam, we take the 970, multiply it again by our pounds per minute, and we get 242,694 BTUs per minute. So the grand total then is going to be 242 plus the original 40,532, and we get 283,226. In 1 hour's time, we would have had 16,993,560 BTUs of heat absorption capacity. So that's what you're dealing with. You're dealing with two different situations of heat capacity going on simultaneously. Think of latent as happening later on. It's attached to the BTU, but it doesn't happen until a certain phase in the heat absorption capacity process. So you've got to get the water from its initial temperature up to boiling, and then once you get it to boiling, then you're able to take advantage of the water's greatest heat absorption capacity and put out fires once you get it into the conversion of steam process. If you see steam happening, you're taking the greatest amount of absorption capacity that you can out of your nozzle. And look for part 2, and we'll see you on the next one.